Welcome to the deep dive. I want to start today by asking you, the listener, to just picture a scenario you've probably encountered countless times.
Oh, yeah, almost definitely.
Right. So you're driving down a major highway corridor, or maybe you're commuting through the expanding industrial outskirts of your city.
Which are just everywhere these days.
Exactly, everywhere.
Yeah.
And you pass one of those absolutely massive commercial construction sites.
Mm-hmm.
You know the exact type of site I'm talking about?
Mm-hmm.
It might be a towering new semiconductor manufacturing plant or a sprawling logistics warehouse.
Or one of those massive mixed-use commercial centers going up.
Yes, exactly. And you see the physical reality of it, right? The tower cranes operating hundreds of feet in the air.
The heavy earth-moving equipment just completely re-sculpting the terrain.
Yeah, the endless grids of exposed structural steel and, I mean, the thousands of cubic yards of concrete being poured. It's this incredibly impressive display of physical engineering.
It really is.
But when you look at that site, what are you actually observing?
That's the real question.
Right, because most people, they just see the physical labor and the raw materials. They see the concrete, the steel, the glass.
Sure.
But beneath all of that physical activity, dictating every single movement on that site is an entirely invisible machinery.
A completely hidden engine.
Yeah, a hidden engine built exclusively out of capital, cost projections, and incredibly high-stakes financial mathematics. And today, our mission is to expose that hidden framework.
And it fundamentally alters how you view the built environment once you recognize that framework. I mean, every single steel beam hoisted into place.
Every hour, a specialized bulldozer is running.
Exactly. Every square foot of foundation poured represents a highly calculated, heavily scrutinized financial risk.
We're talking about projects where the scale is so massive that just a fractional percentage error in a spreadsheet.
Oh, it can dictate whether a development firm achieves a landmark multi-million-dollar success or faces a catastrophic cascading bankruptcy.
It's that serious. And our source material for today's analysis provides the exact blueprint for understanding that risk. We're examining key excerpts from Principles of Commercial Math and Construction Financial Analysis.
It's a fantastic text.
It really is.
Yeah.
But our objective here isn't to just, recite formulas at you.
No, nobody wants that.
Right.
Yeah.
We are going to decode the specific financial language utilized by commercial project managers, heavy civil builders, and corporate financial analysts.
We're translating these core commercial math concepts to understand how strategic financial decisions are actually executed.
In a high-stakes world of industrial construction, yeah. So we'll be covering the fundamental mechanics of profit and loss, the strategic deployment of debt,
The mechanics of operational break-even points.
and the complex forecasting models like net present value that determine whether a billion-dollar project is even viable in the first place.
And we should probably establish right up front that while the text is anchored in mathematics, it's really ultimately a masterclass in critical thinking and risk assessment.
How so?
Well, the numbers are simply the language used to articulate those risks. It's about understanding the underlying rationale. Like, why would a massive commercial contractor deliberately structure their debt utilizing a specific compounding model?
Right.
Or why does a manufacturing facility need to hit an exact, non-negotiable production metric before the equity partners see even a dime of return on their investment?
It's the why behind the numbers.
Exactly. The math just provides the empirical boundaries for human behavior and corporate strategy in the modern industrial economy.
Okay, so let's start with the absolute foundation. The text begins with the core building blocks, basically deconstructing profit and loss.
The basics.
Right, the basics.
Yeah.
So regardless of whether a firm is constructing a state-of-the-art battery manufacturing plant or just paving a regional airport runway, the entire operation hinges on a fundamental binary.
Cost price and selling price.
Exactly. The cost price, or CP, and the selling price, or SP. The text defines cost price as the total money spent to complete the work. It's the outgoing cash flow. And the selling price is the price charged to the client, the incoming cash flow.
Simple enough.
Yeah, the foundational rule is incredibly straightforward. Profit happens when the selling price is greater than the cost price.
And conversely, a loss is incurred when the cost price overtakes the selling price.
Right. Profit equals SP minus CP. But the subtraction itself is rudimentary. The complexity, the real complexity lies entirely in the composition of that cost price.
Because in commercial construction, CP is never a static figure. It just isn't.
No, it's an aggregation of hundreds of distinct, highly volatile cost centers.
Constantly fluctuating based on macroeconomic factors, supply chain integrity, labor market dynamics, you name it.
Okay, let's unpack this. The source material provides a highly distilled example of a contractor hired to construct an industrial warehouse.
It's a great illustrative model.
Yeah. So they break the ledger down into three primary buckets. First, you have the material costs. That's the structural steel, the roofing membranes, concrete, cladding.
All the physical stuff.
Right. And that totals $40,000. Second, the labor costs.
The wages for specialized crews, foremen, safety inspectors.
Exactly. And that sits at $20,000. Finally, you have the equipment overhead.
Rental rates for earth movers, telehandlers, generators.
And that costs $10,000. So aggregating those figures gives us a total cost price, or CP, of $70,000.
That is the baseline capital required simply to physically manifest the warehouse.
Right. Now, the contractor, operating on a standard commercial contract, has secured a selling price, the SP, of $85,000 from the client,
So we walk through the math. 85,000 minus 70,000.
which results in a $15,000 profit.
But what's really fascinating here is that measuring success purely by that raw $15,000 net figure is a dangerous metric for a firm attempting to scale.
Why is that?
This is where the text introduces the vital importance of the profit margin percentage. A $15,000 gross profit is essentially meaningless without the context of the capital risk to achieve it.
Okay, so how do they calculate that?
The text calculates the margin by dividing the profit by the cost price and then multiplying by 100. So 15,000 divided by 70,000.
Which gives us roughly a 21.4% profit margin.
Exactly. And understanding it as a 21.4% margin is what actually allows a business to measure its efficiency.
And that margin on an industrial build, it provides a very specific strategic buffer, doesn't it?
It acts as the primary shock absorber for the entire operation. That margin dictates the firm's resilience to inevitable operational friction.
Because things always go wrong.
Always. A $15,000 profit might sound secure, but in the context of a $70,000 cost price, a 21% margin is actually quite tight when you factor in the realities of heavy construction.
Let's look at those cost buckets again. The $40,000 material cost was estimated before ground was even broken.
Right. So what happens if there is a sudden tariff on imported steel or a regional cement shortage?
Which happens all the time.
All the time. And that drives material costs up by 20% mid-project.
Okay, so then your material bucket jumps from $40,000 to $48,000.
Yep.
Your total cost price is now $78,000. But because your selling price is locked in a fixed contract at $85,000,
your profit suddenly plummets from $15,000 to $7,000.
wow. So your margin just collapsed from 21.4% down to roughly, what, 9%?
Just about 9%, yeah. And that is just a fluctuation in one single bucket.
One bucket.
Now combine a material price shock with a 2-week weather delay.
Oh, man.
Right, a delay that forces you to keep that specialized equipment rented way longer than anticipated. And perhaps it requires paying overtime labor rates to catch up to the schedule so you don't get hit with penalties.
So that original $20,000 labor budget could easily balloon to $30,000.
Easily. And if that happens, your total cost price has now vastly exceeded your $85,000 selling price.
So the CP is greater than the SP.
Which means it's a loss. The firm is literally subsidizing the construction of the client's warehouse at that point.
That's brutal. So that 21.4% margin isn't just a measure of success. It is a mathematical representation of the exact amount of chaos the project can absorb before it becomes a financial liability.
That's exactly it. A slight miscalculation in the labor or equipment buckets can easily erode that margin, flipping a win into a devastating loss.
And that dynamic is exactly why cost estimation and bidding in commercial construction are so intensely competitive. Firms are constantly trying to optimize their operational efficiency to bid lower than competitors, which inherently squeezes that margin.
But if they squeeze the margin too tight, they remove their shock absorbers.
Exactly. And I want to ask you, the listener, to consider your own personal or professional projects here. You might not be pouring concrete or erecting steel, but you are absolutely operating on cost price and selling price metrics.
Everyone is, whether they realize it or not.
Right. When your department commits to delivering a major software integration, or maybe you're just launching a new product line, are you rigorously auditing the true cost price of that initiative?
And that includes your time.
Yes. Time, resources, materials, The direct financial budget, sure, but also the allocation of personnel bandwidth, the opportunity cost of diverting teams from other revenue-generating tasks.
So structural overhead.
Exactly, before determining the value or the selling price of your output. Because if you are only evaluating the projected revenue without understanding the true, fully burdened percentage margin it costs you to produce it,
You are flying blind.
you're flying completely blind. You might be executing projects that are technically successful, but operationally destructive.
It requires a fundamental shift. You have to stop viewing a project as just a single event and start viewing it as a ratio of invested resources against realized value.
Right.
Because if the resource cost is systematically underestimated, the organizational margin vanishes.
Yeah.
And that leads to systemic burnout and unprofitability, regardless of how good the final product is.
Okay, so you have the blueprint for profit.
Yeah.
But let's transition slightly, because assuming the firm has accurately modeled their cost price and secured a contract with a healthy margin, there's still a massive logistical hurdle:
The capital.
the capital. You cannot procure structural steel or deploy a specialized labor force using projected future profits. Large-scale industrial projects require immediate, massive injections of upfront capital.
Which necessitates entering the debt markets.
Exactly.
Yeah.
So this pivots the conversation to the cost of borrowing money: simple versus compound interest.
The mechanics of how a project's debt is structured are often just as impactful on the final profitability as the physical construction efficiency itself.
Because borrowing capital is essentially renting liquidity.
Right. And the terms of that rental agreement can completely dictate the survival of the firm.
So the text establishes the baseline with simple interest. And the formula here is straightforward. Simple interest equals the principal amount, multiplied by the annual interest rate, multiplied by the time period of the loan, all divided by 100. So P times R times T over 100.
Let's use the scenario provided in the text.
Yeah, let's set it up. So a contractor takes a loan of $100,000, that's the principal, to finance the construction of an industrial shed.
The terms are a 5% annual interest rate over a 3-year term.
Okay, so the math is super straightforward. 100,000 times 5 times 3 divided by 100. That calculates to a static $5,000 annual cost to carry the debt,
Which results in $15,000 of total simple interest over the 3 years.
making the total repayment amount $115,000.
Simple interest is highly predictable. The capital cost is linear. It's very easy to model into the project's baseline cost price.
Yeah.
But here's where it gets really interesting. In the reality of large-scale commercial finance, simple interest is a rarity. The text sharply contrasts this with compound interest.
Where the fundamental physics of the debt change entirely.
Entirely. The text defines compound interest as interest that is added back to the principal balance every year.
So it compounds. Let's introduce the compound interest scenario using the exact same loan terms. $100,000, 5%, 3 years.
But the formula changes. It's amount equals principal times 1 plus the rate over 100, all to the power of time.
Right. Because the interest is added to the principal annually, the new equation is essentially 100,000 times 1.05 to the power of 3.
So year 1 generates the same $5,000 in interest. But in year 2, your principal is no longer 100,000.
It's 105,000.
Exactly. The 5% rate is now applied to that higher base.
So by the end of the 3-year term, the final amount becomes approximately $115,762.
Making the interest paid $15,762.
Which highlights the core lesson from the text. Compound interest is always more expensive than simple interest.
Always. Now, on a $100,000 loan over just 3 years, a $762 difference might seem like a negligible premium.
It's basically a rounding error in construction.
Right. But if we connect this to the bigger picture, the text is using this micro-example to illustrate a macro-level threat. Compound interest is an exponential function. Simple interest is linear.
Okay, so let's scale it up.
In the context of heavy industrial development, we are rarely dealing with $100,000 over 3 years. We are talking about syndicating $500 million or $1 billion in debt for infrastructure complexes that might take decades to build.
So if a firm secures a $500 million construction loan with a compounding interest structure, that debt load is accelerating every single year, every single quarter even.
Exponentially inflating the project's cost price. This introduces a massive psychological and operational pressure on the project timeline.
How so?
Think about delays. With simple interest, a 6-month construction delay caused by, say, a regulatory holdup has a fixed, predictable cost.
Right, it's just a linear addition.
But with compounding interest, a 6-month delay in year 4 is vastly more expensive than a 6-month delay in year 1.
Oh, wow. Because the principal is so much larger by year 4.
Exactly. The debt is literally generating its own mass. I've seen real-world examples in massive civil projects where construction delays pushed the timeline out so far that the compounding interest on the debt facility eventually exceeded the actual cost of the physical materials and labor.
The financing structure fundamentally cannibalized the project.
Yes, it completely reframes the urgency of construction schedules.
That explains why contractors will authorize massive overtime budgets, or why they'll air freight heavy machinery at exorbitant costs, or pay premiums to expedite material deliveries.
They aren't just trying to please the client.
No. They are engaged in a mathematical race against the exponential curve of their own compounding debt. If spending an extra $2 million on expedited logistics shaves 3 months off the construction timeline,
that decision might actually save them $10 million in compounding interest at the back end of the loan.
that is wild. It's a constant optimization problem between the physical cost of acceleration and the financial cost of time.
And this connects directly to the listener's daily life.
Absolutely.
Yeah.
Think about mortgages, student loans, or credit cards. Understanding the mechanical difference between civil and compounding rates is the ultimate defense against financial overload.
Capital has a time value, and in a compounding environment, time is aggressively working against the borrower.
If you don't outpace the financial physics of the debt, the project or your personal finances will fail, regardless of how well everything else is managed.
That's the reality.
Okay, let's transition again. The loan is secured, the building is up, and production begins. We're operational. But when does the bleeding stop and the making of money actually start?
That is the multi-million-dollar question.
Right. This brings us to Section 3 of the text. Finding equilibrium with break-even analysis. Because just having a functioning facility does not equal having a profitable facility.
Not at all. Building the asset is simply the prerequisite to the actual challenge, which is achieving operational equilibrium.
The text defines break-even analysis as the tool that tells you exactly when a project starts making a profit.
It's the precise metric indicating when cumulative revenue finally neutralizes cumulative costs, both the initial capital expenditures and the ongoing operational expenses.
The moment the venture pivots from being a liability to an asset, the formula they provide is break-even point equals fixed cost divided by the difference between selling price and variable cost.
Let's enthusiastically detail the factory building example from the text because it perfectly illustrates this.
I love this example. Okay, so first we're tallying the fixed cost for this factory. They spent $200,000 for machines and $50,000 for office setup.
Totaling $250,000.
And we need to synthesize this concept of fixed versus variable costs.
Yes, this is crucial. That $250,000 is a sunk cost. It is entirely agnostic to the operational success of the facility.
Right. Those machines cost the same whether the factory produces one single widget or a million widgets.
Or if it sits completely idle, that liability exists.
Okay, next we have the ongoing metrics. The variable cost per unit. This is the raw materials, the direct labor for that unit. The text sets that at $20.
And the selling price per unit is $50.
So we run the math breakdown. $250,000 divided by the selling price minus the variable cost. So 50 minus 20.
Which simplifies to $250,000 divided by 30.
And the result of that is 8,333.3. So effectively 8,334 units.
The critical concept embedded in that formula is that denominator, that $30 difference.
The selling price minus the variable cost.
Right. 50 minus 20 equals 30. That $30 is the contribution margin. It is the actual margin chipping away at the debt.
This is such an important distinction. When the factory sells its first unit for $50, they don't recognize a $50 profit.
No.
And they don't even recognize a $30 profit. That entire $30 margin is immediately absorbed by the gravity of that $250,000 fixed cost debt.
The factory must sell 8,334 units just to reach zero profit.
Just to break even.
Yeah.
The entire manufacturing process, the supply chain logistics, the sales team's efforts, all of it is just servicing the fixed costs until that exact volume metric is hit.
It is only when unit number 8,335 rolls off the line and clears payment that the operation actually makes true unencumbered money.
Which exposes the immense risk associated with demand forecasting. I mean, the engineering team might design a highly efficient factory, and the finance team might model the break-even point perfectly at 8,334 units.
But what if the total addressable market for that specific widget tops out at 7,500 units?
Then the project is fundamentally doomed from the start.
Exactly. Or consider pricing pressure. What if a competitor forces the firm to reduce their selling price from $50 down to $40?
Oh, wow. Okay, let's run that. The variable cost remains $20, but now the selling price is $40, so your margin collapses from $30 down to $20.
So the new math is 250,000 divided by 20.
Which means the new break-even point is 12,500 units?
A staggeringly different reality. A simple 20% reduction in the selling price doesn't just mean a little less profit.
It forces the factory to increase its sales volume by over 50%, simply to reach the baseline of zero profitability.
It exponentially increases the operational strain.
And I want to ask you, the listener, how do you measure your own break-even points? This concept is universally applicable.
Oh, completely.
When you are learning a difficult new skill or implementing a new system at work, there is always a significant fixed cost associated with the effort and setup. How many hours of fixed cost effort must you put in before the variable ease of the task finally pays off?
Right. When does the cumulative value of the new skill finally neutralize the massive time investment you spent acquiring it?
You have to know exactly where your unit 8,335 is, and you have to have confidence that the payoff is actually there.
If you don't define that point, you're likely to abandon the initiative before it ever becomes profitable, either financially or personally.
Okay, so moving into Section 4. The factory is churning out units past the 8,334 mark. You're profitable. The cash is flowing.
But there is a hidden leak in the ship.
The inevitable decline, depreciation. Physical assets don't last forever.
They really don't. And the concept of depreciation is often misunderstood as merely a tax optimization strategy.
Right, something just for the accountants.
But in commercial finance, the text highlights that machines and buildings lose value over time, and tracking that is a fundamental tool for maintaining the integrity of the firm's balance sheet.
Failing to account for the physical degradation of assets creates a really dangerous illusion of retained wealth.
It does.
So the text lays out the straight-line method formula for this. Depreciation equals the initial cost of the asset minus its scrap value, all divided by its expected life.
Let's go back to the source text machine example to illustrate this.
Okay, so the initial machine cost is $100,000. Its expected functional life is 9 years. And at the end of that life, its scrap value is $10,000.
So the math is 100,000 minus 10,000. That leaves $90,000 of consumable value.
We divide that $90,000 by the 9-year life. That equals $10,000 of depreciation per year.
But this raises an important question. Why do accountants and project managers obsess over a hypothetical loss of value? I mean, no one is writing a physical check for $10,000 every year and putting it into an account labeled depreciation.
Right. If the machine is still efficiently producing the widgets in year 5, why do they insist on recognizing this $10,000 annual loss?
Because acknowledging that yearly drop in asset value is crucial for an honest financial assessment. It prevents a company from overvaluing itself.
How so?
Imagine the firm purchased 10 of these machines. That's $1 million in capital deployed. On day one, the balance sheet accurately reflects $1 million in productive assets.
Okay.
But 5 years later, those machines have endured thousands of hours of high-stress operation. If the financial statements still claim $1 million in assets, the firm is presenting a complete fiction to its investors and lenders.
Because if they tried to liquidate or sell those used machines, the market would definitely not pay $20 million for them.
Exactly. The straight-line depreciation model enforces a rigorous financial honesty. It systematically reduces the stated asset value by $100,000 annually across the fleet.
Reflecting a much more accurate valuation of $500,000 at the 5-year mark.
Right. Furthermore, it forces strategic capital expenditure planning.
Yeah, let's talk about that.
By formally recognizing that $10,000 annual loss per machine, management knows that in exactly 9 years, they will face a massive capital cliff.
The machines will die and need replacement.
The depreciation schedule is a roadmap. It signals that they must retain sufficient earnings over that 9-year period to fund the inevitable replacement cycle.
Instead of just distributing all their free cash flow as profit and then being shocked when the machines break.
Precisely. And the inclusion of the scrap value in the formula is a really fascinating safety net.
It is, because it establishes a hard floor. It acknowledges that even at the end of its useful life, industrial equipment rarely goes to absolute zero.
Right. It might be obsolete for precision manufacturing, but it still has thousands of pounds of high-grade steel, salvageable motors.
Yeah.
Its scrap or salvage value might still be $10,000.
Factoring that in ensures the firm doesn't aggressively overstate its depreciation expense.
Which would artificially depress its reported profitability.
And I want to bring this back to reality for the listener. Think about driving a new car off the lot.
The classic example.
Right. Or even the laptop or phone you might be using right now to listen to this. Understanding straight-line depreciation completely changes how you view long-term purchases versus short-term expenses.
Technology stacks decay rapidly. Hardware reaches obsolescence.
If you view the initial purchase price as a one-time event and you fail to model the ongoing invisible loss of that asset's value over its life,
You will be entirely unprepared when the replacement cycle hits.
you'll face a sudden capital requirement you didn't provision for. Understanding depreciation shifts your perspective from being just a consumer of assets to an active manager of long-term life cycles.
It's discipline over short-term optimization.
Okay, so we're arriving at section 5, the ultimate decision matrix. Because before a single brick is laid, or a machine is purchased, or debt is structured, leaders must look into the future to decide if a massive investment is actually worth doing in the first place.
These are the ultimate gatekeepers for capital allocation.
The text introduces the two final tools for this, the payback period and net present value, or NPV.
Let's start with the simply metric, the payback period.
The definition here is just how long it takes to recover an investment. It's essentially a time-based expression of the break-even concept.
Using the source example, we have an initial investment of $200,000. The projection is that it will yield an annual profit of $50,000.
So the math is just 200,000 divided by 50,000, which equals 4 years.
After 4 years, the project starts making a profit.
This metric is intensely focused on risk exposure. Capital tied up in an unrecovered investment is capital at risk.
Exactly. A project with a 4-year payback period is inherently less risky than a project requiring an 8-year payback period.
Assuming the initial investments are identical, executives want to minimize the window of time where macroeconomic shifts or new technologies could render the investment obsolete before it's even recovered.
But the text implies that while the payback period is a useful initial screen, it's a fundamentally flawed tool for comprehensive analysis.
Because it's completely blind to anything that happens after the payback point.
Right. It ignores the total long-term value, and more importantly, it treats all cash flows as equal regardless of when they are received.
Which brings us to the most complex and critical concept in the text, net present value.
NPV.
So what does this all mean? The text defines NPV as a tool to decide if a project is financially worth it, based on the core idea that money today is worth more than money in the future.
The time value of money.
Let's outline the tricky NPV example the text provides. You make an investment today of $100,000. The future returns are projected at $40,000 in year 1, $40,000 in year 2, and $40,000 in year 3.
The total return over 3 years is $120,000.
So if a project manager just utilizes basic arithmetic, the analysis seems entirely straightforward. You deploy $100,000, you get back $120,000.
A net gain of $20,000.
The superficial conclusion is that the project is a clear success and should be greenlit immediately.
But that seemingly obvious $20,000 profit is an illusion.
And here's why. The text introduces a critical variable, an 8% interest rate.
This is the discount rate, or the hurdle rate. It explains the core philosophy of NPV. Because of interest, inflation, and opportunity cost, that future $120,000 is objectively worth less than having that cash in hand today.
Let's break down that opportunity cost.
A firm possessing $100,000 in liquid capital today has options. They don't have to deploy it into a physically risky construction project.
They could deploy that capital into a highly secure, passive financial instrument, say corporate bonds.
Right. And the text sets that alternative baseline return at 8%.
So the logic dictates that if the firm is going to lock up their money in a risky physical project, the future cash flows from that project must exceed what that money could have passively generated in that secure 8% environment.
The firm must be compensated for taking the risk and forfeiting the liquidity. Therefore, the analyst must discount those future cash flows backward in time to determine their value in today's terms.
You translate the future cash flows into present value using the 8% discount rate. The $40,000 received in year 1 is discounted by 8% for 1 year.
The $40,000 in year 2 is discounted by 8% compounded over 2 years.
And the $40,000 in year 3 is heavily discounted by 8% compounded over 3 years.
When you run that complex discounting math, the present value of that $40,000 received in year 3 is significantly less than its face value.
It's not $40,000 anymore. It might only be worth roughly $31,000 or $32,000 in today's purchasing power.
Precisely. And the net present value is the sum of those discounted future cash flows minus the initial $100,000 investment.
The golden rules of NPV are highlighted in the text. If the NPV is greater than 0, it is a good investment.
It means the project's returns exceed the 8% opportunity cost. It's creating genuine wealth.
But if the NPV is less than 0, if it's negative, it is a bad investment, and it must be rejected.
And this is the critical revelation. An NPV can be negative even if the raw cash flows show a superficial profit.
Because even though the raw returns are $120,000 against a $100,000 investment, if you heavily discount those returns, the present value of that $120,000 drops below the initial investment.
The firm actually destroyed potential wealth by authorizing the project. They would have generated a higher return with less risk by simply parking the capital in the passive alternative yield.
It forces decision makers to weigh future returns against the immediate power of present capital.
It's why you see massive infrastructure projects suddenly canceled by development firms.
Oh, yeah. The public sees a viable project, but internally, maybe central banks raised interest rates.
Yeah.
That drives their discount rate up.
A project that had a positive NPV at a 5% discount rate suddenly shows a massively negative NPV at an 8% discount rate.
The future cash flows are instantly devalued.
And the project becomes mathematically irrational to pursue.
I really want to challenge you, the listener, to apply NPV thinking to your own life. A reward 3 years from now looks great on paper.
A promotion, a degree, a new business venture.
Right. But when you factor in the interest rate of life, your time, your energy, shifting priorities, is the future payoff actually worth the present sacrifice?
What is the opportunity cost of your time? What else could you be doing with those resources right now?
If the net present value of that future goal doesn't exceed your current opportunity cost, you might be destroying your own organizational value, so to speak. NPV forces you to ruthlessly evaluate present costs versus future projections.
It's an incredibly powerful mental model.
It really is. Okay, we have covered an immense amount of ground today. I want to guide you through a rapid-fire recap of the quick summary from the source material just to reinforce the foundational pillars we've explored.
The core concepts.
Number 1, profit and loss. The fundamental binary, driven by the critical importance of the profit margin percentage as a buffer against volatility.
Number 2, simple interest. The linear, predictable cost of capital.
Number 3, compound interest. The exponential liability structure that alters the time pressure of construction timelines.
Number 4, break-even analysis. Identifying the precise unit metric where the contribution margin neutralizes fixed costs.
Number 5, depreciation. The rigorous accounting mechanism for tracking the invisible physical degradation of assets.
Number 6, payback period. The exact duration required to recover an initial investment.
And number 7, net present value. The ultimate strategic gatekeeper, using discount rates to weigh future revenue against the power of present capital.
And remember, these are the indispensable core commercial math concepts utilized in construction projects worldwide. They are the financial physics of development.
They are, and I want to leave you with a final thought to mull over, one that builds directly on the text we've just decoded.
What is it?
Well, the source material provides perfect mathematical formulas to account for the depreciation of machines, the compounding cost of money, and the exact unit required to break even. But what about the unpredictable human element?
The one thing math can't model.
It's exactly. If a massive construction project relies on a 4-year payback period to be viable, how might external changes in the world, unpredictable global events that math simply cannot foresee, alter the value of that future money even more drastically than an 8% interest rate? Math gives us the map, but the train is always shifting.